Thank you for opening up this virtual lecture. Please watch this video and the other video clips in this folder. Also attached in this folder will be a handout that you can follow along and fill in key concepts. Please bring this to Thursday's lecture for your attendance participation grade for today. On Thursday, we will review ahead of our final exam, and we will spend 15 minutes doing the course survey. Lecture will begin with a brief history on Earth. We will go over the major events since Earth formed all the way up to the present day. If you recall, Earth's timeline is cut into 4 eons, the first of which is the Hadean Eon. The Hadean Eon spans from the finalization of the formation of the Earth 4.56 billion years ago up to 4.03 billion years ago, which is the age of the oldest known rock. The Hadean Eon is named after Hades, the king of the underworld. The start of the Hadean Eon is defined as the oldest material in the solar system. These are meteorites. These date back to 4.56 billion years ago, just a few million years shy of Earth's final formation. Earth finished accreting by 4.54 billion years ago. This accretion was known as the early heavy bombardment, when all the planetesimals collided together, fused to form the planets, including Earth. So 4.54 is the age of Earth. Now, early Earth was quite different than it is today. In fact, early Earth was molten liquid, and because of that, Earth differentiated into layers. The dense metal sank to Earth's interior, forming the core. The lighter rock rose up towards the Earth's surface, the bulk of which made the mantle. When the mantle remelted and solidified yet again, that made the oceanic crust. And so early Earth formed 3 distinct layers by density: the moderately dense oceanic crust, the high density rock of the mantle, and the very high density metals of the core. One of the major events during the Hadean was known as the Big Splash. This is the large impact of the Mars-sized body Theia that collided with Earth. This was at 4.53 billion years ago. The massive energy released from this collision melted 100 kilometers of Earth, making a 100-kilometer thick lava ocean. A bunch of debris got flung outwards, and that eventually formed the moon. Most likely, this debris coalesced into a ring, much like Saturn has today, and eventually that ring coalesced into a spherical body, the moon. The rest of Theia was assimilated into Earth, and in doing so, it overall altered Earth's bulk or average composition. It has been argued that perhaps the first oceans on Earth arrived quite early in the Hadean, perhaps as early as 4.4 billion years ago. However, at this time, there are numerous impactors still colliding with Earth, and they probably boiled off the ocean on several occasions. But as we know it today, plate tectonics can only exist with oceans. So as soon as Earth's first oceans began, it's most likely that plate tectonics began. Water arrived on Earth making these oceans through a variety of means. First off, we have water still today that outgasses during volcanic eruptions. So there are volatiles trapped inside Earth's mantle, and when volcanoes erupt, these gases enter the atmosphere. Water vapor would enter the atmosphere and would condense as liquid water running down to lower and lower elevations, making the oceans. We also have found water on meteorites, and perhaps a combination of meteorite impacts and volcanoes have brought water to Earth. Beginning of the rock record begins at 4.03 billion years ago. This is the oldest preserved rock on Earth. And this time frame is known as the Archean Eon. It extends from 4.03 all the way up to 2.5 billion years ago. Arche in Greek means beginning or origin. So this is the origin or the beginning of modern rocky Earth as we know it. Now, during the Archean, Earth was a lot different. Earth was warmer, there was a lot more volcanic eruptions, and the moon was closer, as demonstrated in this artist rendition of the Archean Eon. The boundary between the Hadean and Archean eons was a period of time known as the Late Heavy Bombardment, spanning about 4.1 to 3.8 billion years ago. This was a second large spike in impactors, meteorites colliding with Earth. Everything in the Earth's solar system was hit by material ejected from the asteroid belt, as well as comets ejected from their location. It's believed that gravitational resonance between Jupiter and Saturn led to instability, causing these asteroids to be ejected from the asteroid belt, colliding with everything else. If we look at celestial bodies like the Moon, or Mercury, or Pluto, the vast majority of them have a lot of craters, and these craters stem from this time frame. If we look elsewhere at other solar systems, we can see this as well. For example, at the Eta Corvi solar system, which is 59 light years away, it's about a third of the age of our solar system, and it's currently going through a similar late heavy bombardment as well. It's been hypothesized that the first volcanoes on Earth stem all the way back to 4.4 billion years ago during the Hadean. But with the arrival of volcanoes on Earth, that led rise to the formation of the continents. In fact, during the Archean, the stable interiors of current continents formed. These are known as cratons. The cratons are made up of two distinct parts. First is the shield. The shield is the crystalline basement rock, aka metamorphic rocks, which underlie the continents and are exposed at the surface of the Earth in the centers of many continents. Surrounding the shields are the platforms. Platforms are flat sedimentary rocks which overlie that shield basement. These cratons are largely stable and have not been deformed from tectonic processes in the ensuing time. In fact, tectonic processes have dominated around these cratons, but not within them. On this map of the world, the continents are colored in a strange scheme, but the shields are the orange bits, and the platforms which surround them are the pink bits. All continents have shields and platforms, aka the cratons, in the center of them. question that has stumped geologists for a little bit was, what exactly is a continent? There's a couple problems that arise. If we look at passive margins like the eastern seaboard of the US, the thick felsic continental crust extends into the ocean, making up the continental shelf, where we have very shallow water, and then we have a slope where it transitions to the oceanic crust, which is thinner and more mafic. How do we define that edge if there is a transition? A second problem arises when we look at island arcs. For example, the Aleutians or the Marianas Islands or the Lesser Antilles, South Sandwich Islands. When we look at these, as well as we look at hotspots like Hawaii, Easter Island, and places like that, these oceanic island arcs and hotspots resemble continental crust a lot closer than resembling mafic oceanic crust. So what exactly is a continent? Geologically, a continent must have a craton in the center, or the middle of it. And in addition to the craton, we must have felsic igneous rocks. So when we look around and explore the world, let's look at New Zealand. New Zealand, the island nation in the southwestern Pacific, has two main islands, the North Island and the South Island. But there's a lot more geologically to New Zealand than that. In fact, underlying those two islands is the microcontinent or small continent called Zealandia. And it is a continent under this geologic definition. Has a craton and has felsic igneous rocks. It just so happens to be that most of it is submerged under the Pacific Ocean. So Zealandia is a continent, geologically. If you look at Madagascar, on the other hand, Madagascar is not considered a continent geologically. It is considered a continental fragment instead. It was once part of Africa and has broken off. And inside Madagascar, there is no craton, let alone felsic igneous rocks. And so it fails the two parts of that definition. So Madagascar is simply a fragment that is broken off of the rest of Africa. So to be a continent geologically, we must have that old Archean shield and platform and felsic igneous rocks. Evidence of life dates all the way back to 4.28 billion years in the Hadean. When we look at minerals of this age, there are carbon isotopes in minerals which suggest an organic process. If you recall back to last class, we talked about the proxy methods and oxygen isotopes, how we can figure out past temperature using oxygen isotopes. There, isotopes fractionate, the oxygen 16 versus 18, fractionate between or split between the oceans and ice. Organic processes do this as well, splitting carbon 13 versus carbon 12. So isotopic analysis of really old minerals suggests maybe life began long time ago. But definitely by the time we get to the Archean, 3.46 billion years ago, we arrive at the earliest undisputed fossils. These are found as biofilms, which drape sedimentary ripples. They cover the crests and fill the valleys between successive ripples in sandstones. These biofilms were made by microbes, which were sticky and stuck sediment to them, making a mat. There are places on Earth where we can go to and still have this process occurring. For example, if we go to some of the Keys, there are microbial mats that grow along shoreline and just above sea level, and they stick sediment together. So these biofilms draping the ripples are the earliest undisputed fossils. During the Archean, the first atmosphere formed, and it was a lot different than it is today. In fact, there was no oxygen gas in the atmosphere. Instead, the atmosphere was an extremely reducing environment. The atmosphere during the Archean was rich in nitrogen gas, carbon dioxide, and methane. This is similar to many other bodies we find in our solar system, like Venus. The abundant amounts of greenhouse gases meant early Earth was quite warm. Also found in the atmosphere at this time were ammonia gas, hydrogen gas, and even a little bit water vapor. In 1952, scientist Stanley Miller simulated the early atmosphere, mixing these gases together. And when ignited with an electric spark, amino acids formed. Amino acids are the building blocks for DNA and the building blocks of life. So perhaps weather, a lightning strike, was the source for life. However, since this time, we've also found amino acids in other celestial bodies, including meteorites and comets. So perhaps these amino acids that formed life on Earth came from an extraterrestrial source instead.